Gentlemen, I am again 10 feet tall. Let's see if we can bring it back down. Bring it back down to my level. All right, we made it there, I think. Let's make sure OBS is going to behave. OBS looks like it's going to behave. So, ladies and gentlemen, boys and girls, this is a Pwn College stream. Pwn College's website, you can learn how to hack. It is free and open to anyone. Just go to pwn.college, as it says right here. You can create an account for free and kind of learn some of the fundamentals of computer science. It is set up in a dojo style, so you can click dojos up here at the top, and we have content that starts from fundamentals at a white belt level, following white, orange, yellow, green, and then blue. This content is free and open to anyone, but it also follows along with a series of university courses. This particular stream follows CSE598, which kind of parallels this blue belt material. And today we are talking about kernel exploitation. So, this has been a little bit of a rocky start, somewhat my fault. But we're getting there. We're getting there. There's some good stuff coming, guys. And we are going to take a look at the first couple challenges and kind of begin to reason about these things. So, we launch level 1 here and connect. We are there. Okay. So, on the left-hand side, I am going to look at the contents of the challenge. We have the BZ image, we have the kernel module, and then the Linux image. So we will VM start over here. With the recent changes, it is slow enough where you do want to run VM start, wait a few minutes, and then fire VM connect if you haven't given that a try. Next, I will fire up the old desktop. You know what? Binja is growing on me. I didn't think it was going to, but I'm slowly becoming a fan, and it's not even like anyone's converting me.
Is it local decompilation, or is it also cloud?
That I don't know. But I haven't had it yell at me and say that it doesn't want to decompile for you. So. But we'll have to save that for the fall. See what happens. Okay. So we covered a little bit of this earlier in class, where we kind of described how this thing worked. Just as a quick recap, in a init module, we are going. What are we going to do here? We create the KMM cache for these kernel heap objects. We then do proc create, so we are creating that file known as kheap, which we should have over here in the VM. LSL proc kheap, there she be. And that is pretty much all we got going on in a init module. Now, because we all had our refresher on reasoning about kernel modules and kind of interacting with them via this kernel device or kernel file that's being exposed, we can look at kheap open, which is what's going to happen when we open this file, and we see it's going to print something. It's going to allocate an object from that cache, store it in S, assuming that worked. So if S is not null, S doesn't equal 0, then we will assign S and return. So we're going to allocate on open. If we go into Ioctl, this is where kind of more of the fun stuff happens. What we see here is the first thing it's going to do is copy from user. Looks like 10 bytes from arg3. If we go and look at our man page for Ioctl, we know that the third argument is kind of our undefined miscellaneous blob that we can pass to it. It's then going to switch based upon the arg2 here. Arg2 is the second argument to Ioctl. It's just like a command identifier number. And we see at 5702, we're going to call some type of, we're going to call RAX. So it's going to call some kind of function. It's an indirect function call. We might want to look at the assembly to see exactly what we have going on there. So it is taking the pointer that is at R12, putting that in RAX, and then taking R12 plus 8 and putting that in RDI, and then doing this indirect thunk call. Indirect thunk RAX, this is essentially calling, or an indirect function call, where we are calling RAX, and then what's going on with RDI here? What do we know about RDI when we call a function? It's the first argument. It's not a trick question. We're going to cruise right through. So RAX is this function pointer. RDI is the first argument. And so if we jump back up to our pseudo C here, what we have going on here is this R12 underscore 1. Is arg1 plus hex C8. Now right here, this might look better in IDA. But what do we know about arg1 of Ioctl? It's the file descriptor. And we've kind of seen this pattern before in other kernel modules. Do you recall this? 466? I'm asking for a lot. So right here, we see this R12 underscore 1 is equal to arg1 plus some offset. And then they're doing some typecasting, right? But we've seen this pattern before. Not necessarily this exact thing, because we didn't have the power of Binja then, but we've seen something similar. Like, what happens right here?
Because isn't the first argument to Ioctl a file descriptor?
Mm-hmm.
Is that a pointer to the file descriptor, or is it just?
Is it a file? Is it a file descriptor? So the argument to Ioctl is a file descriptor. Let's see if IDA.
I think I know.
You think you know?
File descriptor, not a file descriptor, but like a file struct.
It.
So like it's doing that plus. It's
The
doing
offset
something
needed
from.
for the struct?
Yeah, that's something.
Yeah.
If I remember, IDA does show this. I don't know if it does on this challenge, but shows it a little bit cleaner. So we end up doing where was I? I was in Ioctl. All right, we got this file pointer. Yeah, so you saw, this is what you saw. So IDA presents it a little bit cleaner up here, where we have that file struct pointer, or that file pointer, just some pointer to represent the data related to this file. And so the kernel module has this private data, right? And so IDA shows it as private data, but this is just some location in memory specific to this open file where we can store things and reference them across all of these calls, right? So we can access this in IDA file pointer private data. We can access this in Ioctl. We can access this in is it going to show it over here in a net? No. It's going to show it over here in open. Yes. So we see on open, this is getting set, right? And so this is just some region of memory that we can consistently access across all of these function calls. Where in Binja, it is just some magic offset, right? We don't get the cool struct dereference. But that is what we are seeing there. Okay. Bam. Back to Ioctl. So there was some type of function call that we could trigger. What do we got going on down here? If it's 5,700, and some number is reasonably small, we call copy to user. What does copy to user do?
Kernel to userland.
Boom. None of these questions are going to be hard. They hopefully do exactly what it says on the can. Yes. Copy to user is going to copy memory from kernel to userland. And remember, it's a destination source. So this is copying to whatever this var30 is. And it looks like var30 is set by us via arg3. So we control this. And where is it copying from? It's copying from that weird R12 thing, specifically index 1. Right? So we have to envision, what does this R12 thing look like, right?
It's in64T, which means that's basically like an 8-byte pointer.
So what does it say? U in 64T? Yeah. So it is 8 bytes.
So
And does it say? It does say pointer. Yeah. So we could trust that.
Or we could GDB it.
We could GDB it. I don't trust decompilation, specifically on types.
Fair.
But because you can just you can claim anything as anything, right? And if you cast it, it eventually works,
It's
right?
always bytes.
Yeah, the compiler will yell at you and say it's a warning, but you can ignore that. Warnings are suggestions. So, but what we do know is that there is at least 8, we know there's 8 bytes before, and then there is this region of memory. It's worth noting here that this is ampersand R12 index into 1. So that is really giving me the address that is 8 bytes into this thing, because it's accessing the array, which would be the literal, and then the ampersand is going to give me the address thereof, right? And because this is essentially a mem copy, it's pointer to pointer, so that's why it's doing that. And then var28 is going to be some count. And if we look at var28, this makes some sense. var28 needs to be not ginormous. If arg2 is either of these and it's really big, we trap, which is a fail state. arg2 is 5701 and we are sufficiently small, we copy from user. This is going to be the reverse operation where we are going from userland to some region of the kernel. And we see we are copying from var30 to that same location, ampersand R12.1 first index. So there's 8 bytes, and then there's some blob or region of memory that we can kind of read and write to via this interface. Okay. This right here looks like a stack canary, so that's not particularly interesting. Right here, 5704. Is going to stir copy. What are you doing? That is weird looking. Because that is saying it's going to allocate something, take 8 bytes after it, and then copy into it. But I thought stir copy, maybe I'm thinking of stir copy n, had 3 arguments. I fell off of my box. Yep, I'm thinking of stir n copy. And it is apparently copying from C30. What does IDA say? Does IDA make that look prettier over in the Ioctl? What was the case? IDA does not look pretty at all. Okay, so in this case right here, That's the 5704. This looks a little bit cleaner because they didn't make it one line. We're going to allocate to v6. We stir copy. Oh, we stir copy the flag. Okay. So we stir copy the flag into 8 bytes past this allocation. Okay. So what capabilities as a recap do we have? We can copy into the kernel, we can copy out of the kernel, and we can put the flag in an allocation. So, if we just think about how Heap works, generally speaking, what is your game plan here? What are you thinking? What questions do you want answered? This isn't, oh, I'm gonna look at you. I had this bad, you hide behind my monitors, right? All right, what are you thinking? Like we've spent, I don't know, however many weeks thinking about Heap, right? We've seen a bunch of different ways to mess them up.
Yeah. Do we need overlapping allocations at all or anything like that?
Do I need overlapping allocations? Okay, so that's a good thought, and what would help us reason about that? We need to think about where these things are in memory, right? Now, I can tell you that, and the description can tell you, there are no protections on this particular challenge. So we don't have KASLR, we don't have any of those fancy kernel heap things going on. This is just memory pointers, things make sense. Right? There's no randomization, there's no random selection. All right, things are going to show up in order as we allocate. Things are going good. And to recap our powers, things that we could do, we could force an allocation by calling open. Now, since this is the kernel, I can open this file multiple times, and that would create multiple allocations because it's all being backed by the same cache. If you recall from class, I showed that you could access this cache thing, and that is what backed all of these objects. So if I opened multiple of these kernel devices, they would all be backed by that same cache. Now, part of that's because this VM is restricted to a single CPU, so everything is the same CPU, so it all has the same cache, and the cache is all backed by the same slab. But just we can assume that we're not adding like those multiple CPU complexities here. So I can allocate something that I can interact with. This allocation is v2, which is our private data, and we go back to the Ioctl. That private data is this private data, which is what we copy to the user, and it's also what we copy from the user. Now, I know in class I was writing Python. Now, I have learned the error of my ways. Okay. Let's make sure I don't have. Good. No, there's always a do.c, guys. Do. Yeah. Delete it. Okay. Having spent some time playing around with the VM and the VM speed, C is the way. All right. So we're going to have some kind of main function. We know we want to call things like, you can't see this on the stream, but I'm just looking at a man page. I've shown plenty of them. We're going to include the headers for open. Read, which should be, yeah. And Ioctl. All right. First thing we got to do is we got to open this thing. So we're going to open proc, is it K-heap, is what we saw. We want to open it, read write. All right, so far so good. Now the act of opening, we said, will perform an allocation. Where is this allocation going to be located? In the heap, that's true. We allocate from the heap. On the kernel, it's going to be in the cache. Specifically, it's going to be in this k-object cache. The k-object cache is backed by slabs. The slabs go to some region of memory. For our purposes, we're going to just assume that it's page. It may or may not be in this case. But because this does not have randomization, it's going to be the first memory location in there, right? So if we think about it as a contiguous, we get like,
You mean like random?
now we're gonna go back and draw our pretty blocks, man. They're always a hit. All right, right now, when we call to open, we own this. We own this block. We haven't put anything there, but we own it.
Yeah.
Okay? What other things can we do? We said we can transfer data into this block. We can transfer data out of this block. Does that help us right now? Not yet. All right? The other thing we can do is we can create an allocation and put the flag there. Is that something we'd want to do? And where would that go in our diagram? There's only 2 blocks, so you got a 50-50 shot here. We own one of them, it's gonna be the other, right? So then if we do this allocation, we can put the flag here. And that was via, where was it? 5704, I think? And Ida put it up here at the top. And so we see this kbm cache allocate, and then stir copy the flag into that location. But it's that location plus 8. This may or may not be important, but let's note it here. There's like 8 bytes chilling right here. And so we can put the flag right there. All right.
It's putting it in that chunk because when we open.
Bad word.
Oh, sorry.
What's the correct term again?
Slab, no, not slab.
Object.
Object, yes. It's putting it in that object because when we opened the KHeap file, it allocated it for us first? Or?
So these are 2 separate things, right? When we open /proc/kheap, that code that's going to execute is right here in kheap open.
Right.
And that is where we see this kmem cache allocate.
Right.
That is this first thing,
Right.
which I'm claiming we own. All right? It definitely doesn't have the flag in there.
Right. And so when we call the Ioctl method to make a flag into object, it calls that malloc method again, which is basically like us calling malloc in userland. And that's like
In this instance, because we are specifically calling kmem cache allocate and specifying the same cache for both of them, and they're on the same CPU, which is backed by the same cache, which is going to use the same slab, which means it's going to be the same region of memory, and it's not randomized, we can make this assumption.
that's why they're adjacent.
That's why they're adjacent.
Okay.
Yeah. But if I, for instance, did open flag, I would just have 3 allocations that I own, and then the flag.
Gotcha.
In this challenge, it doesn't look like we have the capability to free, at least directly. If we looked at, well, let's take a look there. Probably kheap exit.
Is destroy free?
Kmem cache destroy. I don't want to destroy the cache. The cache is everything, man. Right?
Oh, yeah, is it release?
Oh,
There you go.
kmem cache free. Okay, now that would, right? And so that would be, I believe, when we close. What's that? So I believe if we closed it, we would trigger this release. And so we do have the capability to free, but based on what we see here, we probably don't need to At least we don't have a reason to yet. Okay, so we said in our Ioctl, we've made a flag. I'm going to go back to Binja. What other things can we do? We said 5700 will copy to user, and it's going to copy to user. Let's visualize this R12_1 access 1 ampersand insanity. Well, that's just the same looking thing right here, right? We have 8 bytes that we haven't really figured out what's going on there yet. And then this is where we can write. Eight bytes into that object. And we know that from right here, copy from user, where they're using this R12, which is the private data we said, which is that allocation. And then they're accessing it at index 1. The index access tells us it's 8 bytes by going all the way up to the type, where we saw it was, as was correctly pointed out, an int64t or uint64t, which is going to be 8 bytes. And so if this is where the base is, and we're pretending that it's an 8-byte pointer, and we increment it, it's going to be 8 bytes in, and here is our region of memory. So far, so good? Sweet. Okay, our next question is, if we can write here, what are we thinking, how do we get the flag? We can write here, and we can read here. This is our setup.
How is our read limited?
How is our read limited? Good question. Copy from user is our read. The requirement is the length of the copy, so the number of bytes that we copy is less than some ridiculously large number.
Wait, is copy from user, that goes from user to kernel or kernel to user?
Copy from, okay, wait, you want to go for the read. This is file structs all over again.
Yes, it is.
Okay, you want to read from the kernel to the user?
Yes.
Okay. If we go from the kernel to the user, then it's copy to user. Hello there, expert Oni. What do we got? That is, similarly, copy to user. Goes to this var 30, which we haven't figured out what this var 30 is yet. But we copy from that location that we defined, and it just can't be larger than like 32 bits, is what I'm guessing that is. I'm not measuring it. So we can read some arbitrarily large number of bytes starting at this location.
Does that overflow the size of our object?
Oh, how big is our object?
Is that?
How big is our object? And how do we know?
That's a thing.
That is a thing, but like this isn't like, we didn't call malloc, we called this like kmem cache thing.
Is that the size? The 400 cc whatever?
Is it?
I don't know.
Well, what do we know from class? Because we all remembered everything that came out of my mouth, I'm sure. We've obsessed over it all week. What do we know about these kernel caches that's different than userland heap? That,
Every object or every object is like fixed in size?
oh, thank you for the raid, Security Live. So the kernel cache is for a specific size, right? That size could be specific to a object type, right? So here what we are doing is, this is a cache called Heap. And if I'm having bad luck with the internet today. It's the power of tmux. If we cat, what was it? Proc slab info, and let's grep that for Heap object. And if we were to scroll up at the top and reason about what all these things are, one of them is the object size. So from here we can see that this object is 512 bytes in size. So that means that this thing right here is 512 bytes. This thing right here is 512 bytes. And any other alloc that's called against this cache will be 512 bytes. If I want something that is not 512 bytes, I need to talk to a different cache. Cool. So now we have, based on that, we can figure out how much space we have here. It's 512 minus 8. And we're talking about reading from the kernel to somewhere.
User space. Userland. Something you control in userland.
Something we control in userland. It was, what was it, var, was it 30?
The R12.
No, the R12 things are private struct. So we were up here, copy to user, copying from the private data here in R12 into var30. So now's the time to figure out, well, where the heck are we copying this, right? We know it's going to userland. How does it know where to put it? Where's our data going? So way up here at the top, we have essentially a mandatory copy from user. This mandatory copy from user wants how many bytes? 10. Yeah, text 10, 16. Cool. And it's getting it from arg3. Okay. So is this something we control?
Yes.
Yes, it is. All right. So that's going to copy that into this var30. Now what's interesting here is we haven't figured out what var28 is. We know it's the size. I'm going to blame Binja here. What does IDA say is going on with that? Where's the size check here? If, now that's the command. Okay, so IDA is showing it as this. Okay. So IDA's treating this as a struct, the 16 bytes that we can copy from the user, where the first 8, where are the first 8 used?
Can we look at that struct?
I do not know how to use these tools, man. I am a believer in GDB.
What if we double click on K, heap, rec, T? Does that do anything?
That brings us here.
Something local. Oh, there, wait.
You see this? What do you?
It shows us that it's 16.
Okay.
16.
Like I'm sure we can create a struct there, but the struct thing is like, okay, it's 16 bytes and they have some meaning, right? There's 8 bytes and there's 8 bytes, right? Do we really need to make IDA show it as a struct? Or can we say, hey, I understand that 8 bytes are 8 bytes? You want to make a struct? Well, we'll lose an hour, but we can do it.
No, I just want to know where is the size variable?
Where is this size? Okay. So let's see. Well, we only have 16 bytes that we're writing in this thing. Let's.
Like, scroll down.
Scrolling is hard, man. Okay. We are looking for REQ. Okay, offset's 8. So the size is 8 into this.
Second set of 8
Yeah.
bytes.
Yeah, the second set of 8 bytes here are going to be the size. Thank you for the assist there with the hover. And so then what is the first 8 bytes of this thing that we're providing? The buffer, which if we hover gives us an offset of 0. So this is what's going on in the kernel. We have this separate problem of how do we pass information into this bad boy, right? And what we've decided is we need to make the magic request thing. The magic request thing is 8 bytes, followed by 8 bytes. We have a size, and we have some pointer. So far, so good? All right. Where does the pointer go? What? So I have to make this in Userland, right? Because I'm going to have to pass it into the kernel via an Ioctl call. Then the pointer itself should probably go to Userland. Okay, so then the other thing we need, those pictures are awesome, is some big buffer, right? And our pointer is going to look at this thing right here. Buff. You see it in your head? Okay, yeah. They give us all these monitors, and then I still use this dinky laptop screen. You know, what are you gonna do? Oh yeah, I did do good with the camera there. Nice. For once, the camera worked with me instead of against me. Okay, so can we implement this in code? I think we understand pictorially and like conceptually what we're trying to build here, right? All right. So, what are we doing? What do I need? You tell me, I type. You don't have to speak code, just tell me what I'm making. Big buffer, big buffer. Okay, we're gonna go with a page. I like a page, it's a standard size. It's gonna be a char array. What else do we got going on? I need Ioctl, so Ioctl goes somewhere down here. What else do I need? I need to make this this request thing. Now, if we were writing in Python, we could just make bytes and like smash them together, and it would be a beautiful day, right? We're in C, and like you can do some really nasty stuff and like recast arrays as bytes and then as something else and pass around stuff. But the compiler will get really grumpy and it will be quite error prone. So in this case, we probably will actually make a struct in C. And we know there is, I'm going to pull in, and this is a me thing, you don't have to do it this way, standard int, because that gives me access to uint64t. And it's just, okay, this is an unsigned 64-bit value, and that is what I'm going to use as a substitute for pointers. I guess we could, let's see if we can rock and roll with that. Right as I say it, let's do something else. So we'll have buff pointer, and then the other thing in here is our size. Well, you know what? I'm still going to use my uint64t over here. Okay. Can't keep a good man down. Okay. So now I have my struct. Let's make it actually exist. So we'll say, because that's perfectly clear. What do I want to set on my struct? What needs to be what?
Buff pointer needs to be big buffer.
All right, buff pointer needs to be big buffer. Size, what do we want the size to be? A page? All right, we'll rock and roll with a page. I like sizey. All right, what's going on with our Ioctl? We got the open. First argument to Ioctl is FD. Second argument to Ioctl is some number that I don't remember. 570. You're a believer in 4? Oh yeah, we got to get that flag in there. Good call. I wasn't even on that train. 5704. What do I need for the third argument? Do I need a third argument? This is a trick question. I told you there weren't going to be any trick questions, and then I threw one at you. Sometimes it'd be like that, guys. So we go back up here to the top. This copy from user at the beginning, is this something that I can escape? No. This is happening every Ioctl no matter what. So it's going to try and copy into the request. So I probably should give it a request. Because otherwise, if I were to pass null there, it's going to try and copy into null. Right? So I may not really care about what's going on at that point, but I definitely need to just give it to it. And in this case, we'd want it to be a pointer, so we can say, give me the address of request. This call to Ioctl will allocate the flag. I'd highly recommend, as you work on these particularly later ones, to comment your code or structure it in nice functions. I'm still writing C in a Pythonic-like way where it's just this giant blurb, and so comments are very valuable to me. What's the other thing I got to do? So that gets us our flag here, so we have this set up. The last thing we need to do, in theory, is actually, bring it in. So that was Ioctl, FD, what was the magic number? I'm just going to trust you here. And then we give it that same request. Do I need to change the request? Do I need to do anything to it? We're just going to reuse it. Life is great. I'm okay with it. All right. So is that it? I just compile and run this, and we're ready to rock and roll.
We now have a buffer that's filled with a bunch of stuff. We should probably look at it.
Okay. So what we've managed to do is pull a whole bunch of bytes that started from here, and we put them in here in our buffer. So what is our game plan for looking at this buffer?
The naive way would just be print out all the bytes and then figure out what to do.
Okay. I'm going to do a little bit better in theory. I'm going to have do print, and we will include our friend standard.io.h. We're going to rely on printf here to carry us. Okay, so we have a char star buffer. How pretty do we want to make this? Let's define buff size up here so that we just have it as a thing before we have magic constants everywhere. All right, we've got that. So now we can say for int I equals 0, I is less than buff size I plus plus. This is like FizzBuzz, man. I'm gonna screw up FizzBuzz live on the internet. What are we gonna do? We are going to printf %c of buff pointer index I. Right, that feels good. And then if I modulo 8 equals what, 0? And we'll print a new line with puts. And then let's be a little bit fancier. Let's make you printf 0x percent. I'm going to go lx new line. No. All right, we do this. We're going to front load the new line. Then we give it this fancy colon. Yeah, this is going to be great or horrific. And then I. So hopefully here, the first line is going to be messed up, but after that, we will have some type of pretty interface, or it will just be utter garbage because I can't write a for loop. Hopefully this will print it out 8 bytes at a time as hex. Yeah, let's go for it. VCC do.c. I cannot write code. So our first problem is 19. Buff pointer I is undeclared. How is buff pointer undeclared? Oh, I put congratulations, request, you are now a global. Every good programmer uses their globals. All right, request. Request for a buff pointer is not, let's just see if that makes it happier. Did I mistype type def? I did. That is why it's not happy. Among other things. Buff pointer equals big buffer. Request for member is something not a structure or union. That's why I type defed it. If I don't type def, then I do need to say struct rec. So I think it was mad that I named the struct and the type def the same thing, where I should have said like struct underscore t and then called it rec t and then rec type def it as rec.
What? We have naming conventions?
Yeah, you know, someone does. I don't. Clearly. Okay, so we have that. We should have an a.out. We fire it off. Well, that was underwhelming. It does help if you call the function that's supposed to produce output. You'll notice that I'm compiling outside of the VM. You know.
Oh, wait. Oh, I see a flag.
Apparently,
Are there multiple flags or is it the same flag?
yeah. Apparently, there's a couple here. We got one at 1F8. We've got another here at 3F8.
That makes sense. Those are 200, hex 200 apart.
That they are hex 200 apart. So we saw somewhere, and we probably missed it, maybe on a knit or open.
Load the flag in, yeah, in or
Uh,
open. Yeah, there you go.
Open flag, kmem create, yeah. So it does load it in memory there. But, so we ended up having a whole nother one, but we still visualized what we were doing accurately, right? Where we were able to start here and fire on down.
Why is the flag not at 210?
Why is the flag at?
Why is it not at
Let's see here. So what we care about here is 1F8.
Because we're off at 8, right?
I probably can't write a for loop for one, but let's. So we're starting from here, and so we have 512 minus 8, which would be 504, right? Bam. And then this is decimal, that's hex. And then we have another 8 bytes for whatever this was that we didn't care about. So that's 8. It should be 512, which is hex 200. Right? Okay. I'm on board there. What did we actually do?
Or 8 off.
Well-
It might have been.
Oh, is this just I can't write a for loop? I think this is I can't write a for loop. I'm starting at index 0, F8, 512, 104, 512, that should be this. Why am I off by 8?
Wait, you're printing the hex value of whatever we're at after?
I am printing it after.
Oh,
Okay. I can't write a for loop.
Oh, you can write a for loop, you just can't write a print statement inside of it.
Yeah, I failed FizzBuzz. All right, it's out there officially. All right, I can reason about the kernel heap, but I can't pass a basic programming interview question. All right. Sometimes it be like that. So, the offset that I wrote was wrong. I should have put it on the front end, but I didn't want to deal with it because it would make the logic harder. And so instead I just did this. But we see what happened and it makes sense?
Yeah.
Okay.
If we just try to print buff, like index hex 200 directly, will it just get us?
If you print,
Yes.
what do you want to print? What you gotta give me terms I can work with.
If we just like call.
That's
What?
string.
Yeah.
The buff pointer index 200.
Oh, okay. So down here you're saying you want to call printf
Full on string with string.
%s. We'll give it a new line.
Yeah.
And then request buff.
Or I think if we just do big buffer, that should work, right?
Which do you want, guys?
I will request buff.
All right. Cool.
Oh, all right. Request.buff
Pointer.
pointer.
Index.
Seems good.
I claim it is not legit.
All right. Cool.
Let's see if I know what I'm doing. Oh!
All right.
Every once in a while I get them right. We're missing that ampersand, right? Remember when we access the index of the array that gives us the literal, we got an ampersand to get to the pointer. Printf wants the pointer to the location of the characters, not the raw characters themselves. And in that case, yes, it turns out hex 200 is at offset FF8 in Robert's world. Actually, that's because I didn't have another new line, because that last one there is the printf that we added. Sweet. Any questions about what we did, why we did it? There are some interesting things you can do in this level. A lot of the challenges here follow this kind of mechanic or pattern. So it is worth spending a little bit of time looking at, for instance, how the copy from user works. And then we didn't need to figure out, because we used good reverse engineering practices of only looking at things that matter. We didn't figure out yet what's going on with, where was it? The weird thunk. Where's my thunk?
Is it unk instead?
A honk? It should still be a thunk. I'm gonna blame Ida here. See, this is the beauty.
I think in IDA is the jump out pad.
Yeah. I don't know what kind of voodoo that is, man. So instead, I'm gonna look at the over here. We still haven't, and it's fine. We didn't need it for this challenge, right? For what we did, but we haven't really messed around with this indirect thunk. But when we looked at this not as the pseudo C, but as the disassembly, can we reason from this right here how that relates to our pictures? You almost missed today? Come on, man. Like, you are a critical member of the team. Someone has to make fun of me when I mess it up.
What?
No, not you, Twitch. I'm sorry.
I was like, what's going on?
No, I didn't call out Twitch chat explicitly here, but there's one of the regulars almost didn't show. They're enjoying it. It's a good time. But yeah, looking at just this disassembly right here, can we reason about what is occurring?
Yes.
Well, okay. What is your reasoning and why?
I think this command give us control to like execution.
Okay. The statement was we think that the thunk is going to give us control of execution, and that's good. It's a good start. How about you up front? You agree, and why? Related to my pictures. spent a hard time drawing these.
So do you want to draw a new picture? Is that what you're saying?
No, the new picture's for the next level, but we can't get there until you answer this question. Then I can wipe this and draw new pictures.
I think our pointer will be used as like the execute address, and then our size will be the first argument.
Okay, so we said R12 here was, if we go back up to our sudo C, our R12 was our private data, which was, it was this thing. It was the thing we own, right? And so we own R12. We go back down to the disassembly. We are moving the keyword at R12. That's this first 8 bytes here, right? And so this is some sweet pointer. And that's going into RAX. The first argument of a function call is an RDI. What is getting loaded in RDI?
Whatever's right after that pointer.
Just the address of this right here. So it is going to call the pointer that we define with the argument of our buffer. So that is our additional capability here, right? Because if R12 is the beginning of this, then moving the literal that is at R12 moves the literal pointer. And then LEA for load effective address, we are loading the address of R12 plus 8. R12 plus 8 is going to be right here. We aren't getting the literal because we're doing load effective address. And so instead we are getting the pointer to this buffer. All right. Hopefully that was a good time by all. We gotta draw some shapes, think about the heap. You miss Kyle? Kyle's good, man, I get it, but you know, I like to think we have fun together. All right, level 2. Level 2 here says, time to try some real TM kernel exploitation with randomized free list. And there is no win functions. So this is what Kyle kind of left you guys with. I'm not going to erase everything. Actually, I like this. Otherwise, I'll end up redrawing the same shape, I think. Okay. Team Mox. We split. Let's take a look at this guy. What do you want, Ida or Binja? Okay, good. A little bit too slow, but we went the same way. Okay. Take a look at this kernel device, and we have something very similar here. On a init, we're going to make this kmemcache create. It's the kheap object. We're going to create the kheap device at proc. Nothing fancy there. Open. We are going to allocate that first object into V2. V2 ends up being our private data. So far, all of our model that we have here, as far as how this whole shindig works, is holding up. We go into not the underscore guy, but just kheap Ioctl, and we see something, again, very similar. We have this mandatory copy from user, again with 16. All right, we now have a working model, guys, right? Let's make this have some hex. All right. So what do we have now? Well, we lost a critical function.
We lost our magical loading flag.
Okay, so we can't have this thing anymore. Rip. Can we still do this?
Yeah.
Okay.
We can read that all we want.
Yeah, we got the copy from user, and we got copy to user. So we can still read and write, and
What's 5702?
5702. 5702 is casting private data. What do they have private data here as an int? Private data is a void star star. Okay, so that's going to increment by 8. That doesn't look sane, so we'd probably have to look at the disassembly here. And we go to label 5. I don't like that.
Did we run Binja?
Oh, we can binge it. You want to binge her? Binge has been pretty nice to me, man. Somebody says the problem I currently have with level 2 is how to ROP when we got arbitrary call primitive. Yeah, I could imagine that. That sounds like a hard problem. You know, I suffered from this problem too. And together, we can get through it. All right. The first step is admitting you can't figure it out. What do we got? Heap Ioctl.
Oh, our funk boy.
5702. Yeah, see, this is where, come on, man. Binja, that's great. Like, what was Ida's equivalent here?
Label insanity.
It casts the buffer to nowhere, sets some result to 0, and then jumps down to nowhere.
Five's at level, the line is one.
Oh wait, label 5. Okay, that's all the way down here. Yeah, which is still nowhere. Like Ida didn't do a very good job there. Trying is the first step to succeeding, is what you mean to say there. Okay, so we have our thunk. We can make our allocation. Let's copy, what was this, do.c to do2.c. I think we got some good bones here, right? We've got my do print that doesn't work. We got our buffer. A lot of this stuff still makes sense.
We can no longer allocate.
All right, we can't allocate the flag. This one here was reading from kernel to user. We can't do that anymore. We probably don't need this at the moment. Right, like we can. So at this point, what we know is we have the allocation, and we can read right to it, starting from here, and then we can also trigger the magic thunk. Okay, do we happen to know where the magic thunk goes? The magic thunk is going to go to wherever RAX is, because it's indirect thunk RAX. We don't see it there, but I thought we saw it in the, yeah. Okay, so the magic thunk is controlled by this pointer. What is this pointer normally? Because we don't control that pointer, right? We control this pointer in our request. All right, our request determines what userland buffer we're playing with when we move stuff back and forth. But everything that we move into and out of starts here in front of that pointer. So I can't get there. So what is the old challenge putting there is the first question. Let's go back to our sudo C, proc entry, proc create. I don't see anything on init. Is it on open? There's the allocation. If it doesn't equal 0. Oh, yeah, all right. Let's see what IDA does in open. Okay, that is my allocation. My allocation is V2. If V2, so if we didn't allocate nothing, like we got a pointer back, we are going to null out, looks like hex D8 bytes, and then we set this pointer to be do print. They stole my function, man.
What does
Do print calls print K.
All right.
Where does print K go?
D-message.
Pro tip, if you want to see that output, don't call dmessage inside of the VM, call VM logs outside of the VM. One of those will be significantly faster than the other.
All right.
Yes, somebody here on Twitch points out REX is do print by default, which is this amazing print K. All right, it's going to print whatever this says that I can't read. Heap %s, K heap, and then %s. So that's probably not correct that there's one argument there since we have a format string. Probably takes 2, where the second one is that string. But do we need to fix that right now? No, we just say, all right, Ida, I got you. All right, what's our plan of attack here? What are we thinking?
Well, if we had like sequential things again, like here we could just like overwrite X chunks,
Okay.
magical pointer thing of where to go, but we don't have sequential chunks anymore, do we?
I don't have, well, let's go back to Ioctl. Let's see what we can do. We have the ability to read from the user. We have the ability to read from the kernel, and we have the ability to call, right now, this is do print. And we can call do print.
Yeah.
Is there anything else we can do?
We can open more things.
All right, what happens if I open more things?
More objects are created.
Okay, more objects are allocated. I'm gonna remove some of our fancy red there. It was hot while it lasted. It was a fleeting moment. So, this challenge, the description said that it has randomized free list. So, in my picture here, what happens when I call open? We know when I call open, it's going to trigger kheap open. That's going to call the kmem cache alloc. All right, so that does give me a new object. Is it guaranteed to be from this slot? No. So I'm going to keep the red. All right? I think the red it has some flair. I'm just going to go for 4, because that's what I got. Can we know how many slots are there in this cache at the moment? Can we say that 4 is right or wrong, and how do I know?
There was a thing, the proc thing you could look at.
Yes, the magic proc thing.
Case line info.
So there's a few magic proc things. The one that I'm going to say is what you probably should do is just cat proc slab info. That's the raw feed of it. There are other tools that refer to proc slab info and another reference and formatted a little bit prettier, but those tools also sometimes work and sometimes don't. And tooling is iffy. Like in class, you guys asked, or somebody asked about, hey, what tools are there? You know, what can you throw on the dojo? I threw some things on there, and these were the things that worked more often than not. And one of them still only works like sometimes. Right?
Sometimes the magic stuff is that.
Sometimes the magic smoke goes out. That is very true. Okay. you know. So over spring break. All right, I'm gonna be typing Windows Start for the rest of my life. Yeah, unfortunately. So I do need to be root, but we can cat imagine Windows 1 core no KVM. Yeah. Cat proc slab info is what I was going for here. This has most of the goodies. There was another tool, but that is not officially installed on the dojo at the moment. I may add it later. So we were looking for, happens to be up here at the top. What do you know? Okay, heap object. So active objects, it says 0. Number of objects, 0. Object size, 512. Objects per slab, 8. Pages per slab, 1. Num slabs right now 0. Num slabs was the second from the end, right here. So we have to be careful about our word usage here, right? Or else the kernel guides will come and smite me. So recall that a cache is supported by slabs. A slab may be a page. It may be multiple pages, but there can be multiple slabs that support the cache. And so right now, have we, in level 2 here, have we allocated any K-heap objects? No. So there's this cache, but does it need to be backed by any slabs? No. We haven't asked for anything, right? It turns out that if you were to, say we were to allocate some stuff and then free it, and then we wait some amount of time, right? If they are slabs that are not, have no allocations, right? All slots are available, probably the wrong word. That slab can be freed from the heap by the greater kernel memory allocation. So if the kernel itself says, hey, I need more memory, it can ask the heap, and in turn, all of these caches, hey, if you got any like slabs you aren't using hanging around, like let's give them up, right? And so it's totally a reasonable state for there to be 0 slabs here, right? Because we haven't done anything with it. So what we do know, though, objects per slab, 8. Pages per slab, right now it says 1. So if there's 8 per slab, pages per slab 1, 8 sounds like a number, right? So 4 wasn't right, 8 sounds like a number. My strategy here, what is this, do to? Do to. Oh no.
You've made the critical error.
Yes, exactly. Do not do that. Even Vim can't keep up with the power of the VM. Okay, so now we are outside the VM. Somebody says, FYI, Cropper is installed on the dojo and good for kernel gadgets. This is true. Cropper is, we're going to get there. I installed Cropper on the dojo. Bam, bam. That tool works. +1 for Cropper.
Why do you need K, not just 1?
So the kernel's big, right? If we were to look at, right, this is our giant ELF file that is the kernel. But is everything that is in this image, all 398 megs of it, executable things that we could like reason about for ROP gadgets? It's not. Like everything isn't, you know, a reasonable ROP target, even on a userland ELF, right? There's read-only memory, there's the BSS, there's other sections of memory in our ELF, right? And this Hopefully I'm not a, yep. This is just an elf. It's just a really big elf. And so that means that there are plenty of sections that we don't want to reason about there. And so if I were to use, and it's not only that, as we'll see, ROP Gadget on this, it takes a minute because it is quite a large deal. Apparently it's going to take, this isn't in the VM. This is just ROP Gadget chilling.
I don't know, how long would you take to analyze 400 megabytes of assembly?
Well, I'll tell you what. This may or may not print out something, but if it does print out something, it's not going to be accurate. Okay? However, if instead we use Cropper, which is a multi-threaded ROP guy here written in Rust,
Hello, old Rust.
it's plugging along at a good clip. They found lots of good things. And the addresses that it provides will be correct.
Oh, interesting.
So that took 5 seconds, where ROP Gadget took more than 5 seconds to even begin to do something. So that,
I don't have K-Romper installed. I just have ROP.
we're on the dojo, man. We all get K-Romper. All right. If you do want to like get it yourself, we graciously stole this from good old Zolatool. I did give them a heads up because they have their own fork of it. Did I miss it? Aha. They have their own fork. I'm literally just ripping this and throwing it up on the dev tube. So if you want to have it locally, this is where it's coming from. And so it's fast, it's accurate, and somebody that does kernel exploitation on the regular is maintaining that fork. So hopefully things won't break. Cross your fingers. All right. Back to where we were. We said we can create new objects here, but we have no guarantee on the slot that they come from. So how do we want to deal with this?
What if we just fill up the entire thing?
Okay, so let's modify our logic here. Let's have FDs. We are fancy with FDs. For I equals 0, I less than 8, I plus plus, and we'll say FD's I equals open. Cool, we did that. Now we can stop and like look at things in GDB if we want at any point, but if you can play with pictures, it'll save us time. So in theory here, we now have filled all of our beautiful guys here. We own these. We own. What do we want to do now? And why? And obviously this is wrapping around.
Well, we want to overwrite the magic address in one of these things.
Okay.
Tell the kernel to do something. No.
We want to overwrite the address of one of these things. We want to tell the kernel to do something. Twitch chat chimes in here with either write to all the FDs and call 1, or write to 1 and call all. Both of those are valid approaches, right? We could start from here, overwrite, start from here, overwrite, and in theory, you've overwritten all of them. Then if we call any one of them, it should result in an overwritten pointer getting used.
Right.
That is good for this case. We could also, as they say, overwrite 1 and then call all, and 7 of the 8 would result in do print. 1 of them should result in whatever we've overwritten. I'll propose a third method, right? Not needed for this challenge, but is worth just kind of considering and thinking about. What if I overwrite 1, but I write past the pointer to where I can observe which one it is, right? So if we said that we know from prior, assuming we haven't changed our K-heap objects, right? We could write, instead of hex 200, write hex 208, and then put, I don't know, Pwn College or pizza time, whatever we want as our kind of signal value in the object that we can observe. Because then we could detect and determine it without having to execute all of these arbitrary things, and we could do it without potentially corrupting other values that may be problematic. There's 2 ways that you can kind of fail the kernel here. One of them will result in oops. Let's see, I don't think we've done such a thing yet. We have not. If we aren't far enough along to mess stuff up well enough. But if you were to, for instance, cause the kernel to seg fault, you've probably done this, definitely in 466. You get that nice printout in D message that says, these are your registers, RAX, RBX, whatever. Here's all of the values, here's something else, and it gives you a call stack, right? That's an oops. That is, generally speaking, a recoverable scenario. The kernel says, hey man, like something bad happened, we'll let you know, but we're gonna try and roll with it. The other thing that can happen is you can kernel panic. And if you kernel panic, that means that you messed up so good, the kernel's like, we can't, it'll print out some info, and then it's just, we can't continue, right? And the entire VM will lock up. You'll see the output in the VM logs, and unfortunately at that point, the answer is VM restart. There is no coming back from that one. Both of them can occur. One of them can be useful. Because remember, if you do the oops, it can print out register values, which may or may not be helpful. I know in one of the 466 challenges, that was one of the interesting things.
Like the stack pointer?
Yeah, we did something like that, where we use that output. You could use that output to reason about addresses in the kernel, right? And so that same kind of thing can happen here. Somebody says, code calligrapher, have a good night. Thank you, you as well. Other question here from Twitch, does the allocation of the caches change on each run? How can we know in advance I didn't get your approach? So there's 2 questions there. The first question was, do the allocations, and I'm assuming you mean the order, do the order of these allocations, say it's 1, 2, 3, 4, and then I bail out and everything cleans up nicely, I start up again, will the order of that change? The answer is yes. It could then be in order, 1, 2, 3, 4. Every time you run it, the order of these allocations is not known. What my approach was I still said allocate them all, right? Allocate all 4 of these. In our code we have 8, in our picture we have 4, same idea. I pick one of these at random, doesn't matter which one. As long as it's not the last one, then this logic will work. So I have a 1 in 4 or 1 in 8 chance of just failing, right? But assuming that I win my roll, right? I can start writing from 1, overwrite the pointer, and then write past it. And the reason I may want to do this is I'm only corrupting or overwriting 1 object, right? I don't have to overwrite multiple objects, because maybe, like in this challenge, it isn't an issue. But maybe overwriting this pointer has other implications, right? Based on the behavior of how the kernel's using it or the module's using it. So maybe I really don't want to mess up too many of them. I could overwrite one of them and then place in this other buffer area that we own, A, or B, whatever I want. And since I have the ability to read from here, I can then, instead of looping through and like calling all of them, I can loop through and read all of them, which is essentially a no-op. I'm not corrupting more data by doing a read. And so I can observe my A here and then know which file descriptor corresponds to the corrupt or the overwritten pointer. So that was hopefully answers both of those questions. All right. So what do you guys want to do? We hit you with 3 approaches. All should work. They're all reasonable takes.
Put in a flag string, or not flag string, but obvious string. Figure out what you do.
You want to do that? That's the harder logic.
Then you do some things really wrong.
Dude, I don't get paid for fancy code. I'm not sure what I get paid for. They keep paying me, so I keep showing up. So we got our fancy loop. This is where I want to read. We're going to pick one at random. So let's say 4. 4 is a number. We want to write to this one. How do I do a write? Ioctl. Fine, we're going to guess 5701. And then I still want request. Request is still set up to go to big buffer. Do I need to fix up anything here? We're writing a page? So the buffer's a page and we're writing a page. What do you want to write?
X200.
Is that really what you want to write? Where does hex 200 get us?
Oh yeah, we want to write more than that because we want to put some stuff after.
Right. If you want to do that technique, we'd need to write at least 201. But 208 is a reasonable. So I'm keeping the buffer big because maybe we need that extra space in the future. I'm just setting the size of our request guy here in Userland to be 208. Okay. We do. Okay. Now, what do I want to actually write? How do I control that? We set the size. How do I set the values?
We dump some stuff in big buffer.
All right, what do we want in big buffer and how do we want to do it?
Well, we don't care about like the first hex 200 bytes-ish, except for that last 8 bytes.
Okay.
We don't care about anything except the last 16 bytes, basically.
The claim is we don't care about anything except the last 16 bytes. I'll roll with it for now. So we want to set buff pointer, which is just a char star, plus. Okay, we're gonna do some fugly C here. All right. You want 1F8. Is that right?
Yes. Yeah, because this should write the
F8 gets us to here, 8 more gets us to the pointer, and then 8 more past that gets us into what we can see. We agree?
Yeah.
All right. So we want that location.
If we send it somewhere random, the kernel should segfault, right?
If we
If we set that pointer to like somewhere random that's outside the kernel, we should get a segfault, right?
this pointer here is buff pointer, which points to here, which is still in userland,
Yeah.
plus 1F8. So it's pointing somewhere here in userland.
Right. And if we set the value at that pointer to some random address, that'll get copied into the kernel page, right?
As long as it's a valid address, yeah.
Okay.
Like a valid userland address, it would get copied in. Okay, so I have this guy right here, which I'm then going to cast to be a uint 64t star,
Yes.
which we will dereference and set equal to, what do we want? This is our pointer here.
Yeah. Where do we want this pointer to go?
I don't know, where do we want the pointer to go, man?
I'd say so somewhere random, so we just see if we get a cycle.
Okay.
Do the old Heap.
Oh, classic. All right, the other thing we want to write is our signal value. It should be this right here. And we will go with
We have 8 bytes. Okay, yeah.
another classic.
Yeah, there you go.
Exactly.
Say 1337.
Yeah, I was going to go with that, and I was like, nah, let's do something different. So in theory here, one of these, we have overwritten, we haven't really like set these. In fact, these bytes aren't known, really. As a good habit, there's no guarantee, it probably is, that the buffer is null.
I think when you call a Heap open, it zeroes out everything.
When I called Cave open this is, I'm talking, okay, I pointed to the wrong thing. I'm talking about the
Oh,
userland
yeah,
buffer
yeah,
that we're
yeah.
about to yeet into this thing, right?
Yeah, that's true.
So we have no guarantee, technically, that this buffer, userland buffer is 0. So do we want that to be 0?
We should zero it out.
Okay. So we will memset big buffer to be 0 for buff size. What does memset want? Is it string? It is string. Eventually, you write enough of these and you start remembering them. I used to think Jan was a wizard, and then I started reading main pages, and then this happened.
Then you became a wizard.
I just look like a wizard, all right? It's all an illusion. Okay, so we've set this. And so one of these should be set. We want to observe the value, so that's going to be, we loop through them. We call Ioctl on FDI. What was it?
5701.
5.1? It's mission critical to get this one right. Copy from, is that what that's?
That's writing.
Yeah, 5701 we did up here. This is where the comments come in, man. Right? We're doing the right here. And so this is loop through and check for.
We have it written down there, reading from kernel user.
We do have it written down there. Unfortunately, I can't read past what I'm typing, so it's a problem. All right. How do we feel about this?
Wait. Aren't we just gonna, oh yeah, we should put a check in there. It's like, otherwise we're just overwriting the same parts of.
Okay. And we will need both of these things. We probably want to call strcomp on this monstrosity. No. What do we want? We don't want strcomp. F, the monstrosity. Equals. No, this is some C code, man. Okay, if the monstrosity equals that, let's print F found it at I. All right, let's fire off with this and see if we got the logic right. Buff pointer is undeclared, probably because buff pointer is part of request. I could have referenced this as big buffer as well, right? Because it's the same memory location. Either would be valid. FD should be FDS, because I'm a believer in plural arrays, which is a bad thing. Let's make sure. Yep, that one's just a suggestion. And we go. Huh. Well, that isn't really what the check I wanted, is it? Because I don't want to, it said I found it at 4, but of course I found it at 4 because I'm looking, I wrote it to 4 and then I said, where is it? It's at 4. That one wasn't a big surprise. I probably want to see where it starts at. I want the context there. Memcomp? No. Okay. If I did memcomp, I'd have to put cafe babe somewhere and then reference it. What is this? Some operations on memory. We are messing around with kernel exploitation and the kernel heap. At the moment, we're trying to overflow from one slot to another, and we are failing to detect it. Let's see why. What do you want?
Checking the value, we just print out all of the.
Okay, you don't trust my.
Your valid C code?
Right, totally valid C code. And instead we will print out, what do we want? OXLLX at index D, and then this becomes request buff pointer. Expecting LLX, but it's a char star. Yeah, get bent. It's a pointer. Okay.
The fact that they're all the same makes me think that is that the address of do print? We're failing to overwrite things.
Is it constant? It's not. Let's see. Where are we setting? Request buffer, which is a char star, right? I just want to make sure we're not like doing some crazy ink there. We do the addition, we do the cast, dereference it, we set it to a value. That makes sense. And we're not seeing either of these. Well, we could reason through this, or we could bail early. Oh, I missed something here. Twitch says, you don't know what you stumbled into, but you don't think it's a level 100 course. It is not. Somebody says, you're doing memset 0. Doesn't it end reading on null? Well, that's a question. Copy from user. Well, it doesn't say anything there. And is there a man page? I don't think there is here. There is not. But we can man copy from user, and it does in fact exist. number of bytes to copy. No, it just rocks and rolls. We don't care about null bytes. And for our print here, we are just using a pointer. So that should be good as well.
Can we print the 8 bytes after where pointer points to? Just see if we have like an off by 1-ish error.
Sure. Reasonable. The amazing thing to me is we haven't.
Oh wait, no, were you just putting out the address of the pointer?
Yeah.
All right. Cool.
Yeah, the C code was wrong, but not in the way you expected. You were scared of all the parentheses, right? It's never what you think it is.
Okay, this makes more sense to me. It's still not correct, but it makes more sense to me.
Okay. Things are getting tricky here. What do we see? Twitch has got me. Yeah, you're still bagging on me for memset. You want address of request pointer. No, printf for LX should be the literal, if I'm remembering correctly. Isn't all code some operation on memory? Yes. Deep. All right, what else do we know? You know what? I'm going to abandon this for now in the interest of time. And instead, we'll trust Twitch chat.
Spray and pray.
We will spray and pray. All right, so let's loop through and write it. We only want to write dead beef. So that will overwrite all of them.
You want to change the 4 to 9.
I do want to change the 4 to a 9. Then I will do the thunking. Right? Hopefully. What do I want? We'll just pick one of these guys at random. And what was our thunkening number?
2.
OX5702. Still give it a request because it has to have that. And then just for giggles there, let's print a couple things. If we make it. All right, we were killed.
Excellent.
Let's VM logs. What is this? Oops. The kernel says, oops.
Yes.
Something bad happened.
I mean, we caused RIP to jump to deadbeat, so we did the thing we wanted to do.
All right, so we did do the thing we wanted to do. Oh. No, it wasn't what I thought. Dang. Dang it. I thought I forgot to update the size. Okay, but yeah, right, so we are able to overwrite one of these. All right, and that's great. Do we notice anything else from here? Well, no. But there was something else we could do, and we saw it when we were looking at level 1. This is where we binged. Are we at thunk? Yeah, this is thunk. So, oh, that's the return thunk. That's not the thunk I want. Heap Ioctl. Where's my thunk? Right there. Yes. Remember, we also set RDI to be this value here, to be our pointer to the buff. We don't really see that necessarily. I don't know. Where's RDI? RSP, eflex, RBX, no, that's RDX, RSI, R8, R10. I can't,
Oh, wait. It seems like, no, there's an RDI, like 8, like way off to the right.
oh.
Cut off or something. Do we want to do like the analogs at the end, maybe?
Good old buffering. Okay. Yeah, I'm gonna carry on the ampersand debate. One day we'll figure out why I can't write C code, but not today. So now the question is, what do we want to execute? We don't want to execute dead beef, right? Kyle's stream was very, very useful for giving hints here as far as what we want to do or what we could do. He mentioned a few things. One of them was from 466.
You mentioned run command, but also said that run command doesn't exist anymore.
Okay. Do we want to run the command that doesn't exist anymore, known as run command? Does that seem viable?
Like the code exists places, but we can't call it like directly, or we can't like just say run command. We have to figure out where that code lives now.
So we could find run command and maybe jump to it because it's been inlined, right? So that's an option. That may be a bit time consuming for our constraints. Anyone else see Kyle's stream? Have an idea?
So we do commit cred with prepare kernel, whatever.
Oh yeah.
All right, we talked about good old commit cred, kernel, whatever.
Yeah.
All right. So what was the commit cred kernel whatever? It's okay. We can admit it's been a while. You know, we can go back here and be like, Jan, you know what? There were in fact some words of wisdom hiding in here. We were talking about privilege escalation. It was a different time. Okay. So back in 466, we learned about prepare kernel cred and commit creds. So we could, is it on the next slide? Yes, combine the two and do this. Do we have the capability to do this? What can we control right now? Let's go back, think about primitives. Like what do we have access to influence? So we can control one call, right? So we can call whatever.
As well as the first argument to that?
Is that what we set?
We included an address to start all the rest of that object.
You know what time it is?
GDB time?
It's GDB time. All right, I got my man pages in. We got to get some GDB. It isn't right if we don't do both. It just doesn't feel right. Okay, so I'm somewhere arbitrarily here in the kernel. How do I figure out where I want to be? If I want to figure out what's happening right here at the indirect thumb. All right, I want k-all sims. I do need to be in practice mode because I need to be root. So we sudo cat proc k-all sims grep. What am I after?
For commit creds?
I'll go with challenge. You just say it confidently. If you say it confidently enough, even if you're wrong, you're right. All right, that is the secret. Well, what I want to do is I want to look at, because I want to look at right here. I want to understand what can I control, right? And we could like reason about it from the disassembly, but we could also pretty easily throw GDB at this if we're smart about how we do it. So Heap Ioctl is what we're after. So I can now break in GDB. Twitch claims we control call and RDI, and I say you are wrong. Okay, so we could just set a breakpoint right there, right? But we could also examine, say, 90 instructions at that address, because I can be more precise than that.
Oh, I saw our thunk boy.
You saw the thunk boy? Now you won't always get these symbols, particularly in, I think, the next level when KASLR is enabled, at which point now you just have call address, and you're in for some fun. What you can do to reason about that, which I definitely think is worth mentioning, is take your amazing tool, look at the function you're interested in, count the number of calls to what you're after, because your static analysis tool will be able to know where it is. Your dynamic analysis tool will not because of the randomization. So in this case, we aren't dealing with that problem yet, so we can set a breakpoint at that location. We continue onward. Now I'm going to change our source just a little. I want to set the beginning of buff pointer to be Cafe Babe. Should be the same effect. I'm just writing it at the early part instead of the later part. You follow?
Would that affect the thing that we're calling?
Well, so what I want to do is I want to put something here instead of having it be null. I don't know that it's null, right? But in order to tell what I can influence, I need to put something there so I know what I'm influencing, right? If I just say, yeah, man, I can control RDI, it's like, sure, but like, show it. So this should result in a value being placed at the beginning of the buffer that we should be able to observe in GDB. And so we'll either see that in RDI or we'll see that somewhere else, and that should help inform us of what's going on. All right, bring GDB back up. We fired on the left over in the VM. We snagged our breakpoint over here on the right. Notice that was pretty pain-free. Aside from reflowing that layout, we are at our thunk array. So what are we interested in? RAX. RAX is dead beef. We knew that. We knew that from the oops. What's the other thing? Well, Twitch claims we control RDI. Is that Cafe Babe? That is not Cafe Babe. We do not control RDI. What do we control? What's the difference between P and X? P prints the value in the register. X will dereference that address and show the value at the pointer. So we don't control RDI, we control the value at RDI. You're correct, I don't see any values, and my code is horrendously flawed, as we've just seen. Good job, Twitch. All right, so I don't control RDI, but I can control the value at RDI. What was our thought here from Jan? Well, we wanted to call prepare kernel creds with an argument of 0. Do I have the capability? That's my first step in this. Do I have the capability of doing that?
You can do that, yeah.
I can do that with what I have right here.
Oh, wait.
Do I control RDI?
No, you just control what RDI, or you control control whatever the address that RDI points to.
I control the value that RDI points to.
Yes.
Yeah, you were going in the right direction there, yeah. So I can't set RDI. And in order to call prepare kernel cred 0, I need to control RDI, but I don't have that power. Instead, I can control, I'm going to call it RDI or star RDI. Some horrific new syntax I've just invented, right? Hopefully that tracks. All right, so that is problematic. Now there's two things that Kyle mentioned, and he mentioned them a little bit kind of in passing offhand. It wasn't nearly as direct as what I'm going to throw at you. I'm not gonna finish this, but I'll leave you to ponder a couple things. The first is something that Kyle said. We go over into our trusty source. We are on 679. And what were we calling? Prepare cred? Prepare kernel cred, right? Prepare kernel cred. Sometimes, man. Okay, and I'm interested in the function here. Prepare kernel cred, if we pass it an argument of 0, then this task struct is 0. What it will do, let's see if we can find it. Old, new, atomic, old, new equals old, new, get cred, daemon, 0. Let's look at that. That looks like where things are coming from. Have I gone too deep? Cred equals task cred task. Come on. How about the macro? Is it a macro? Task real cred as a member. Oh no. Real cred. That's where it's defined.
I feel like we might be too deep in the sauce.
Oh, I know where it goes. Okay. The initializer goes to init cred. I didn't know I didn't know this was the happy path. I knew where it goes, but I've never chased it all the way down. Bam. So there is this initial credentials that are the default. And so the reason that prepare kernel cred 0 results in a root credential is because that you get the default credential. And the default credential is the root credential. But, as we saw as we chased down the rabbit hole here, the default credential actually exists somewhere. We talked about the elf not being entirely executable. That's because there's other regions of memory, there's other sections. One of them should have this init cred thing. So I'm going to go ahead and segfault from here so that I can get access to proc kall sims. What? There's a symbol for this initial credential. That's interesting. I could examine that in GDB. I could see what those values are, right? Would that result in like a default credential? Like, we can see what a default credential is.
That would result in something that we could mock up within our big buffer and then send to commit credits.
That's something we could do. So the statement was we could use our knowledge here from GDB and looking at this to imitate what is there in the default cred and just make our buffer that we copy copy in, look like the default cred. Then I don't need to call with argument 0, do I?
But would that only work for practice mode, so we can examine init cred in practice mode, or would that carry over into?
The init cred is the init cred is the init cred.
Okay.
The memory location, in this case, would actually be constant. But if we had KSLR, then the memory location of it would change, but the values of it should be constant. Don't hold me to that one, but that's my understanding. So that's one thing we could do. The other thing that was mentioned was a particularly tricky and funky, what was it? Do CPU work function? Yeah, is it in there? Work for CPU function. I just want to put do in everything, man. All right, work for CPU function. And this one, he was just like, it's a thing, it has gadgets, and it's good, right? And then he's like, stream over, because somebody asked the question about like a driver's license or something. I was like, okay. But I was curious, where he was going with this, right? And so if we grab this address, let's examine, 40 instructions that are chilling right here. Oh, that was way too many. It's not a very big function. And what do we see going on here for our gadgets, potentially? What's interesting are lines 8 through 16. Actually, no, 5 through 16. Now, you'd have to look at it and think about it for a little bit. And remember, we don't control RDI, but we control the values at RDI. And so this provides like an interesting way to kind of change how that power works. I'm not going to explain it. I'll leave that to you to look at it and think about it. But you can do what was originally suggested, or you can think about how this particular series of gadgets from +5 to +16 relate, which could also be worth looking at in GDB because it's a cool little series of gadgets. So you could set a breakpoint here, set the location that you're jumping to be there, and see how these values move around. And that may also help you kind of reason about what it is that you're dealing with there. Yeah, somebody said I only saw it in source, but now you get it. That's because GDB is the ultimate tool for every occasion. All right. Anyone have any questions? I think I wanted to get through the first two. I had as optimistic we'd get to touch on the third one. Didn't get there. We'll leave that for future lectures. Any last minute questions while we're on stream? Nothing? All right. So hopefully that is enough to get you started, get you kind of thinking about this, get you working on the material here. I had a final sanity check. Question from a high level, what did I just watch and where is step one to start understanding any of this? Fantastic question. All of this entire lecture, what's being streamed here live, is a class that's being ran out of Arizona State University. Now this is a advanced class, which is why it's like, what the heck did you just say and show me? But you can follow along through all of the material that builds up to what we are doing right now. All you have to do is go to this website, Pwn College. All right, it is free and open to anyone, so you yourself can create an account. All we ask for is an email and a password, and that's just so that when we reset your password, we can email it to you, right? We don't use it, we don't spam you, there's no cost, right? We want people just that are interested in this stuff to be able to learn it. And as it says here, welcome. It kind of gives you a great how do you get started. Here's a little kind of introduction dojo. The whole thing is structured kind of in a martial arts style with a series of dojos. And so this is the kind of bare bones, how do I use the dojo? And if you click here, you'll see, all right, we've got a getting started lecture. These are all pre-recorded by the various instructors, including myself. And you'll see there's some written words here. Everything that you've seen me do is interacting with this website, with this Dojo platform. You do not have to use SSH, which is what I'm using here in the terminal. If you want something a little bit more user-friendly, you can click either workspace or desktop here. The workspace gives you VS Code right inside your browser, where we can have a terminal and start kind of learning some of these things. And the desktop will give you a full Linux desktop that you can work on these challenges here. The dojo as a whole is structured not only with getting started, but a series of topics here. So we start off with fundamentals, which is kind of like getting familiar with the terminal, a lot of terminal commands, kind of thinking like a hacker and how to abuse behavior of programs. We then go to a junior level class here, Intro to Cybersecurity. And this is where we kind of explore a number of cybersecurity topics, web, binary analysis, cryptography, some networking stuff. It's all very good stuff. And then we have two more belts between the beginning and what you just saw. The yellow belt and green belt, which focus on program security and then system security. This right here is a little bit of system security stuff because we were kind of messing around with the kernel. And then our final content here is software exploitation, which is what you just watched. And our current topic that we are discussing is kernel exploitation, which is this right here. And so anyone can create an account and check out these videos. We also have a Discord that's linked to on the main page there. You're free to join, ask questions, talk with other people that are working on these problems, and hopefully you too can learn how to hack. With that, anything else? You guys want to get out of here, so I am going to hang it up, Twitch, because people want to escape the rain. With that, I'll leave you all. Goodbye and good luck.